Thank you. Listening to the previous speakers, I was wondering where was the general equilibrium everybody talks about and uses, including in modeling. And so my presentation will have as an objective to present a world where are much more non-linearities than linearities, where there are much more disequilibrium than general equilibrium, and where the usual approach based on microeconomics may be somewhat irrelevant. So I'll start by explaining the origin of the term topodynamics. Topos in the Old Greek means location. That's simple, okay? And dynamis in the Old Greek means force. So it is an approach that is based on location forces, and it is a very Weberian approach. I'm a Weberian. I may be the fourth Weber in the list of Peter. Peter said he had 3 Weber. Tellier means in French, in Old French, about Weber. Yes, it means weaver, as Weber means weaver. Okay, I may be the 4th one. I'll present the evolution of my thinking, and I have to tell you right away that my approach is very non-conventional. Very non-conventional, okay? Let us start with the Weber problem. So I introduced a new generalization of the Weber problem a long time ago, and I introduced the notion of repulsive forces. So I've called the new problem the attraction-repulsion problem, and it is just the Weber problem, which was the Fermat problem at the origin. So the Weber problem is a generalization of the Fermat problem, and the attraction-repulsion problem is a generalization of the Weber problem to repulsive forces. So when I introduce that type of force, I attempted to see what was the effect of this in terms of location and development of location systems. And here I show you one of the very first tests I've made. It is on a very isotropic space, and you generate attraction-repulsion problems, and you solve them. You choose the reference points randomly, and you choose also the value of the forces randomly. But here we talk about the interdependence effect. What is interdependence? There is interdependence when the reference points of the new problem is based on some optima or optimal points that have been solutions of previous problems. So you generate hundreds and thousands of successive problems, and there is here I equal 33% means that 1 out of the 3 reference points that are selected, 1 of them is chosen between the previous optimal locations of the previous problems, okay? So 67% means that 2 out of the 3 new reference points are chosen amongst the previous optimal location, and so on. But you see the extremely obvious effect of this. the more interdependent the problems are, the more polarized the system that results is. And you see at the end, with the 100% interdependence, you've got an extremely polarized, it is like an urban system. It is really like an urban system. I must say something very important from a theoretical point of view. In this simulation, there are no agglomeration economies, nor diseconomies. Most people think that the main explanation of polarization is agglomeration economies and diseconomies. It's not the case according to me, and this is the proof. There is no agglomeration economies at all in this, okay? Second image. So we introduce, we keep the same given interdependence effect, and we introduce repulsive forces. The effect is not clear in terms of polarization, but the effect is clear in terms of location of polarization. If you look at the highest level number or frequency of repulsive forces is A equal, but I've been told that I better use this here. Did you say this? So in this image, you see that the polarization tends to be around in the frameworks. So, and there is a very important effect of any repulsive forces that are introduced into the simulation. So the more repulsive forces there are, the more the periphery of the delimited space is favored by polarization. And the less repulsive forces there are, the more polarization takes place in the center. As we have seen previously, the polarization took place somewhere around the center of the space. Here is, I've made a simulation of the conquest of the West. So the difference between the two images is that there are 1,000 iteration in the above figure, and whereas there are 1,000 more iterations in the second one, and you see that there is movement toward the west. So at the origin, at iteration 0, there was only 5 cities, the one located on the eastern coast, okay? And progressively, the movement goes westward, okay? So, many years after that, I went to Congress in Lisbon, and European geographers presented that map that was my road to Damascus. They presented the spatial distribution of production in Europe, and it was very centralized. And I've been extremely struck by that because as a Ph.D. in regional science, I could not explain what I was seeing. There was no theory I had learned that could explain this. You have in front of you a continent where are dozens of countries that have been most of the time at war, have been at war with each other for centuries. You've had extreme rightist governments and extreme leftist governments, and there is a kind of invisible hand that did this. How do you explain this? And then I realized that it looks very much like the simulations, a very theoretical one I had done in the past with the Weber problem. And then the same geographers presented that second map, and I was struck by the fact that there are a kind of linear pattern in the distribution of European population. And it is oriented from northwest down to southeast. And I've been struck by the fact that a good part of the history we learned at school is in this part. If you look at this, Britain, the Netherlands, the Rhine region, northern Italy, Rome, Greece, and if you go on, you end up in Mesopotamia. So I said, my God, how come? This is what I've learned at school when I was about 8 years old. How come? So, but I'll come back to that later. A few years later, I was given a mandate to produce urban projections for Cameroon in a very difficult context. The only available data were the following ones. We had an administrative inquest of 1967 giving the population of the various districts without any indication of sex and any indication of ages. And we had a second source of information. It was a normal census of population, distinguishing between sex and age groups, but it was made in 1976. We had no birth rates, no fertility rates, no migration data, nothing. So I decided to go back to Weber, and I imagined a very funny model, the most unconventional. It is not econometric. There is no dependent nor independent variables. There is no statistical test, and it works. And so it has been applied at the various scales, metropolitan scale, regional scale, or national scale, continental scale, and world scale. And every time we produced projections of population and projections of the evolution of the spatial distribution of productions. And it is based on the kind of simulations I had made earlier in a very theoretical isotropic space. So it is based on interdependent attraction-repulsion problems, and it has 5 parameters. So the parameters is, well, let us say the first one refers to a kind of a gravity model, but it is the effect of the deterrence effect of distance, okay? So we can reject some randomly selected problem because it involves too great distances, okay? The second one is very important, the parameter that refers to the range of repulsive forces, because repulsive forces have an explosive effect on the distribution of the various points. And left, oh my God. Okay, okay, so the problem is to find the value of the 5 parameters that are such that we can reproduce on a computer the observed evolution of a system. locational system, both of population, of production. And the main problems were to find an index of global conformity, and we, at last, after several attempts, we found a solution, and we have an index of global conformity, and we found a way to optimize the model with NOMAD, which is a non-smooth optimization by a mesh adaptive direct search. And now it is completely free of any analyst intervention. We had a project comparing and trying to integrate classical new economic geography, econometric models. What I would like to stress is the fact that the topodynamic model is focusing on intercausality, on loops, on the fact that, and this is the first presentations where stressing the fact that there are what I call chicken and egg logic that are developing and that seem uncontrollable. And the concept of topodynamic inertia, which is also very important in the topodynamic model, is based on the interaction between the actual locations or addition or subtraction of existing locations and the virtual or the virtual optima when you are changing. And this explains the movement towards the West in North America. Every time locations move towards the West, it changes the optimal values of the different criteria. So virtuality is change at the same time that reality changes. So there is a loop that is created between. It's a chicken and egg effect, and it is extremely frequent in modern world. And the more we advance, the more we are faced with that kind of. And in my opinion, the traditional concept of general equilibrium leads nowhere. It leads, and one of the results of our comparing the two approaches, we attempted to make a link between the evolution of production and the evolution of population. And my conclusion is it is better to treat them separately, because logically, in a general equilibrium system, the highest population growth should normally correspond with the highest production growth, and it is just the opposite we observe. It is just the opposite. So, oh my God. There is another tool I would like to talk about. It is gravity field. It has been explored in the past, but there are many things we can add to the traditional way to approach that field. And in my paper, I am presenting at the end the biggest problem we had to face in our applications were the fact that we have not statistical definitions of what a city is. Oh my God. This is, I proposed a kind of a urban metric system, and I think, I have to prove it, but I think that right now that it would be possible to impose statistical definition of, in terms of limits, geographical limits of the different areas, and what is a city in terms of the difference between urban and non-urban, urban and rural, and so on. And I cannot understand that after so many decades, not to say centuries, we have still no definition of what a city is. People that are studying urban sprawl cannot even say in what proportion the area of the city grew. This is ridiculous. But we are, all of us, we are guilty of that. So I'm suggesting a way and resorting to the notion of gravitative fields. But I must say that I pretend to have found a kind of justification of my topodynamic corridors based on gravity fields. It's a marvelous demonstration I wanted to show you, but I have no time. Okay.
Yes, perhaps, perhaps in answering some questions, you can show us a few more of the slides. And I'm sorry to have to rush things along.
No, it's okay.
Some interaction is always good. Yes, Saskia.
I propose that you show it as
Yes,
part of an
okay.
answer to my question. I don't need to ask.
So the first corridor, the great corridor, the one with it's the history we have learned at school. It starts with Mesopotamia, right here, and then Greece and Italy and so on. Okay, up to no, it corresponds to the highest densities of population. So those of you who know about Ravenstein's law of migrations, development leaves traces of population, okay? And so by gravity potentials, we can estimate in a mathematical way the tracing, okay? And now, the American corridor, which is dominating the world right now, all the great cities of the world are in that corridor. Well, let us start with Boston, and New York, Los Angeles, London, Berlin, Moscow, here Beijing, in Korea, Seoul, and Tokyo. This one corresponds, you see the vectors. The vectors, it is, you are an African, for instance, okay? And you are attracted by the largest productions that exist. So you have all the points in the world, and you see the vectors, the kind of tails correspond to vectors. And everything, everybody wants to go. In South America, they want to go to the United States and so on. And you see that the vectors are pointing towards that American corridor. And the American corridor had been computed on the basis solely of history. And it is maybe 10 years later that we made the gravity field analysis, and we put the two together, and my assistant could not believe what he saw, but I was triumphant. And, and the third one, the Asian corridor, which is very important, it is the one that surrounds the Himalaya. So it's the Silk Road, continental Silk Road and maritime Silk Road. And you see the vectors here close to the Asian corridor. Suddenly it goes towards the American corridor, whereas inside it goes towards Shanghai. There is a kind of a vortex inside of this. This was quite, I could not believe it. Why? Because half of the Asian corridor is in the sea. and there's nothing that attracts in the sea. I could not believe this. But the Himalaya has an impact, and it corresponds with different exponent. The previous one with an exponent of distance of 1, and the second one, the exponent of distance was 2. Okay? In my book, I make an illusion without the representation, without the image. Okay? Thank you.
Okay, other questions? Yes. Just a second.
In fact, Doxiadis in his book, I'm sure you know, in 1965, Acoustics, talked about a range of different city sizes all the way up to things that were not yet imagined, sort of. And in some sense, it'd be interesting to compare your table with that. I mean, you may have done this, but my point was not really that. It's that one of the reasons I think people have found it very difficult to define cities, apart from the fact that the concept is ill-defined, as indeed urban is, and so on, is that cities have clearly grown. We probably all agree that they've grown. I mean, really, until the Industrial Revolution, you could never really get a city more than about 1 million because of constraints on technology. And it's quite interesting that normally, if you ask people, if you look at the received wisdom on city sizes, the biggest cities in the world are Tokyo at 33 million and, Mexico City at about the same, 25, 30 million. In fact, the Joint Research Council, as ISPRA, have just produced, within the last couple of years, a database which looks at urban agglomerations, which is particularly interesting because, again, it shows this notion that as population increases, the definitions change, and the biggest cities in that are the Pearl River Delta is the biggest city with about 43, 44 million, followed by the Shanghai, sort of Suzhou, even Nanjing kind of greater region. So I think the interesting thing is that it's all kind of relative to how big the total amount is in that sense. It'd be interesting to see whether your theory has extended to that kind of dynamics, really.
But the main problem, in my opinion, is the fact that the definition of cities is changing over time, including in a given country. So when you try to produce projections, you are based on things that are not scientific. So we need a definition that would make the estimation of the city populations relevant or at least coherent.
So let's have one more question.
One small thing.
Yeah. Yes.
What kind of effect if we do not have if we do not have a definition, right?
Yes.
So we have different kinds of definitions. What kind of impact does it have on the ranking system that we are using?
It means nothing. It means nothing.
Peter, why don't we take Peter's question and then we'll have to respond.
Take that one.
Yeah.
Get the microphone. Good. Well, thank you, Luc. I've read your book on the urban world history, which I really found fascinating to go through. What is it, 500 pages or so? But it's a fascinating book. I have a question on your world maps and the topo dynamic corridors. I'm always concerned about empty spaces, and I see Latin America, I see Africa, etc., empty, Australia, etc. So wouldn't it be possible to have the same type of analysis for continents, for countries, so get some sort of a fractal system of different cities? So you might start off maybe even with districts and have the same topodynamic corridor system within cities connecting districts in a city or neighborhoods in a city, and then maybe urban regions. Could you build it up from almost scratch, almost individual units, up to a worldwide picture by way of some sort of a fractal analysis of all these forces?
But I must say something about the meaning of those corridors. The corridors are they correspond to the locus of the various cores that have dominated throughout history. So it doesn't mean that regions that are far from a corridor are very poor. It's not really the meaning. It is really, I say that there is a kind of generation of cores that Babylon generated to some extent Athens, Athens generated to some extent Rome, and so on and so on. And the succession of cores corresponded to, in the case of the Great Corridor, it corresponds to a chain of seaways or rivers. Important, the Rhine River, the Thames, the Rhone, the Po River, and so on. And the American Corridor correspond to the rideable ways for horses, and later with railways. It is a flat land without almost no obstacle, no forest, almost no river or important river to cross, and so on. And the last one, the Asian one, correspond to the Silk Roads. So they correspond to something really concrete that has been described in the traditional history.
Okay, well, thank you very much, Luc.
You have to
I'm
read
sorry-
my
sorry,
book
we
to have all the details.
Yes.